did just briefly talk about the first part of 3.2. Does that look familiar? Corner, cusp, vertical tangent? No?
Yes. No.
Okay, well, we'll review it because it's been a while. Okay. So,
Do we have a different schedule Friday too?
yes, we have class tomorrow, or not tomorrow. We have class tomorrow and Friday. What's that? No, just Friday. And this Friday, you just have F and D switched. So instead of D, you'll come to F. Everything else is the same, so it's not like last Friday. Okay, so differentiability. Real quickly, there were four reasons why a function would not be differentiable at a point. One is if you have a discontinuity. Okay, you can't find the derivative at 0 in this case because from the left and right they have different values. Okay. Next one was a corner. So this is where the left and the right hand derivatives, they're different. Okay. So if they're not the same value, so here from the left it's -1, from the right it's +1, but it is a continuous function. Yeah.
Anytime there's like, if it's like a piecewise, if one is x squared and one is, like if it's a different power, will they always have different derivatives?
Not necessarily. They could.
But if it's like an odd and even power,
It could still work out. Yeah, so you could still have a piecewise function that initially when you look at it, think there's no way that they could have the same slope from the left and right, but then if you go through the process of the, doing the limit definition, you still could get the same derivative from the left and right.
even if one side is squared and one side is just x.
Yeah. I can give you an example then.
Would it be a corner if one side is curved down and the other is just
Would it be a what?
a corner if one side curves down and the other side is just one?
Yes. Yeah. Okay, cusp. So we talked about this is when you have a rational function, even over odd, where the even is less than the odd power. And we said that a cusp is specific because it goes on one side, the tangent or secants are approaching -infinity, slope, and +infinity from the other. And then finally we had vertical tangent. This is when we have odd root, or like x to the 1/3 if you think of it as that, as a rational exponent. Okay, so they both of their slopes go to +infinity or both go to -infinity. Okay with that? Okay, so let's look at an example. So let's take a look. This is a piecewise function. So we want to look at this point 1, 1. Okay, so from the left and from the right, we want to find those derivatives. So let's do from the left. So the derivative of 1 from the left. So that means we're going to use, right, so this is going to, so from the left we're going to use the x squared.
You can choose to do the h approaches 0 or the x minus.
Right, so you can do, I prefer for one-sided limits to do the h approach 0 from the left. So we want f of 1 plus h minus f of 1 all over h. Both of them are going to look like that initially. It's just a matter of which one do we plug into. So from the left, we're plugging x squared in, and then from the right, we'll plug into 1 over x. So what's that look like? Okay, so what happens? Yeah, so the ones are going to cancel. So you have, well, you'll have 2h plus h squared, right? So if I factor out h, we're left with 2. Okay. Okay, so from the left, this slope is approaching a slope of 2. Now from the right, we can clearly see that they're not equal. But again, to just kind of show that algebraically, that's where we want to plug into the limit. So now we're going to do the same thing. You don't have to write this out every time. I'm just trying to show you that we're doing the same thing, but now plugging into the right function, the one on the right, that's going to be what? 1 over 1 plus h minus 1 over 1 all over h, right? So now what do we need to do? We're going to multiply this one by 1 plus h over 1 plus h. Question? And what do we have? Yeah, what's going to happen here? You're going to have 1 minus 1, so that's going to cancel, and then distribute, so we have a negative h over 1 plus h. And then instead of multiplying, or instead of dividing, multiplied by 1 over h, so these cancel. What do we end up with? Negative 1. So since we got from the left a slope of 2, from the right a slope of negative 1, right, so okay. Any questions there? It's a little, I know it takes a little bit of time to show. I wrote in pretty much every step. If you skip a step or two, that's fine. Okay, so differentiability implies local linearity. So what does that mean? The idea of differentiability is kind of zooming in closer and closer to a particular point. So if we take a look at this example of parabola, so if I were to just zoom in more and more into a particular point, what happens? It starts to look like a line, and that would happen to any part of the graph. So what we want, again, is from both sides, it to be looking like some type of straight line. It doesn't have to necessarily be horizontal. I just so happened to zoom in at the vertex here. Okay, and if I were to zoom in even more, it would turn out to be more and more horizontal. If you were to zoom in on a different point, right, and zoom in more and more, again, it's going to look like a straight line. So what we're looking at for differentiability is that we're kind of zeroing in on that one specific point. Does that make sense? Okay. So, do we have our calculator today? Okay, so I'm going to show you how we can find derivatives on our calculator. There's a few different ways. Okay, so I gave you the example. Let's say we have the function x squared, and we want to approximate the derivative at 2. So in other words, we're picturing, like if you have, here's y equals x squared, so here's 2. So what is the slope there? Okay, remember the derivative. The derivative. Okay, there we go. The derivative is just the slope. Okay, so first thing you could do, if you go to your math button, number 8. So if you see, in this class, we're going to be using number 8 and number 9 a lot. Obviously, this is the derivative. 9 is integral. So we'll use that more December. Okay, so number 8. Now, it depends on what version of the calculator you have. Most likely it looks like this. Anybody's not look like that? You have an 83. Okay, so older model. This is how you're going to type it in. Oh, that says it. That's supposed to be a, sorry, that's supposed to be a 2. Right there. Okay, so go ahead and type in what you see here. So it's blinking right here. So you're going to just type in X, and you can just type in the variable X.
Is it always going to be X?
Is it always going to be X? So what I will tell you is the letter doesn't matter as long as the letter that you use here, here, and here are all the same. Okay, so you could, technically, you could change all the letters to A. You could change them all to Y. You have alpha, and then you have your letters in here. So your calculator will differentiate depending on whatever variable you tell it to use. Okay, it's not really that important. I mean, do we always use X? Yeah, I'm almost always going to just type an X in there. Moses, you have a question?
Oh, yeah. So, isn't,
I don't know what you're going to say either. Maybe we'll come back.
oh, okay. So, like, you know how you can get, like, what it is with an X instead of plugging in the number? Like the formula of the line at that point or at that. Do you know what I'm talking about?
What is he?
I know what he's saying.
What's he saying?
Like when you don't have a
Translation.
a number to plug it. You know how like sometimes you ask us like instead of plugging the number to find the equation.
Yeah, if you have a TI-89, it'll do it for you, but not a TI-84.
What's a TI-89? What is this?
It's a more complicated graphing calculator.
I really want to get it now.
How much is it?
But you can't use it on... What?
Is it like
It's the same price, I think.
TI-89?
The 89 is not very user-friendly. The 84 is much easier to use. Not to say that you can't learn to use the 89 or the TI Inspire you could use also. It'll do the formula. But
Doesn't have, like,
but remember, most of the exam you can't use your calculator for. And so like the chapter 3 test, half of it, like when I ask you to find the derivative, that's going to be on the non-calculator part for a reason. So I will show you can graph them, and it just won't give you the formula. So what you would do here, so now you're going to plug in. We want to evaluate this. Remember how I said this line means evaluated at? So we're taking the derivative with respect to x of x squared, evaluated at x equals 2. And then press enter. Now we get 4. Right? Okay. So f prime of 2 is equal to 4. So if we look at the graph, yeah, we can kind of picture that that looks like a slope of 4, approximately. And then if you have the older model, you have to just type in like comma x, comma 2. Okay, next, graphing. Okay, so let's go to your y1. So that's usually the quickest, easiest way to check your answers if you're just trying to find the derivative at a particular point. So what I want you to do is I want you to type in x squared. And then we can just graph it however, maybe in standard. I just graphed x squared. y1 equals x squared. Okay, so step 2, you're going to press second and then the trace button where you get to the calculation. Okay. You're probably used to this because you've done value, you've done 0, minimum, maximum, where they intersect. 6 is your derivative, 7 is your integral, which we'll do later on. So if you press 6. Okay. Now, all you need to do is type in the x value you'd like to evaluate the derivative of. So if we just type in 2 and then press enter, it will give us dy dx equals 4. Okay. So there, you can graph derivatives. So let's say you wanted to graph the derivative of this function. Okay, so you would just type into y2. You'd go here. Now, I want to do the derivative of, now you can type in x squared here, or maybe I don't want to have to type the function in, so you want to type in y1. So, oh, sorry. Hold on one sec. Oh, I forget the shortcut for some reason, but if you go to variables, and then go over to y variables, there's a shortcut. I'll show you how to do that when I remember. So if you go to function, it gives you all your y values. So what you can do, of course, it was probably easier just to type x squared, but sometimes you have a really lengthy function.
Oh, you could have just typed in x squared.
Right, you can just type in x squared. It's the same thing. I'm just saying sometimes you have a very complicated original function, and there is a shortcut. I just don't remember it at the moment. So I think it's alpha something, and I don't remember which one. Alpha. I'll figure it out. X evaluated at every value of x. So if we graph it, let's see. This is our derivative. Okay. So this is actually a way that you can check your answers on, if it's a calculator OK section. You could figure out what your derivative is and then plug it in and see if you get the right graph. I'll explain when we get to that later on. The slope at any point. Right, and so these y values are changing. So this is, the blue one is our original function. Okay, so if I take away, let's say I take away this,
You might have to change it to y.
let me just graph the derivative. So the values on the line represent the slopes on the original graph. So for example, if I wanted to figure out well, of course, so if I wanted to figure out, why is this not working? If I wanted to figure out the value at 6, I get 12. So that means on my original graph, at when x is equal to 6, my slope is 12, the slope of the tangent. Yeah.
What was the point of drawing the red line if we already got the derivative from the graph? We got the derivative.
I was just
You're
yeah, there's multiple ways to get the derivative and to get a tangent line. And then I'll show you later on you can actually draw a tangent line on your original graph at a particular point. But I don't want to give you too much. Okay, it can get a little overwhelming. Okay. I think this is our last, is this our last page of notes for, or is there another page? Oh, there's another page. Okay. I just want to make sure we have enough time. Okay, so differentiability implies continuity. So if you know it has a derivative, then the function has to be continuous. However, if it's at a particular point, if I say it has a derivative at a, then it has to be continuous at a. The other way around, not true. Because we have these exceptions, corner, cusp, or vertical tangent, which we had on the first page of the notes. Okay. All right.
Wait, what did that mean? Sorry.
If it has a derivative, then it's continuous.
No, I got that part. But like
If it's continuous,
for the example, so any of the examples on the first page don't have a derivative.
that's correct.
Okay.
So if it's continuous, that does not imply differentiable.
So it's
And that's not to say that it could be differentiable. It just doesn't mean that it always implies differentiability.
Are differentiability and like derivative like the same thing?
Yes.
Okay. So,
Differentiability, it means that you can find a derivative.
got
So you have to see if it's differentiable to see if you can find a derivative. Okay, so here's an example. Here's a piecewise defined function. At what domain points does the function appear to be differentiable? That's part A. Part B is continuous but not differentiable. And then C, neither continuous nor differentiable. Yeah.
So for A and B, all points except for x equals negative.
Oops. Right. So for part A, well, wait, which one did you say here, Gillen? You said all points except,
And 0.
oh no, there's a bunch, there's more.
Oh, and 0.
So what we're going to look at, what are we going to look at for it not being differentiable? We're going to look for where it's not continuous. We're going to look for any corners, cusps, or vertical tangents.
Not continuous at x equals 0.
Okay, so it's not continuous at x equals 0, so we know it's not differentiable here.
That thing at 1.
Here it's not differentiable.
where?
And what about here?
Wait, so it's 0 and 2?
There's 3 places where it's not differentiable.
X equals 2, x equals 0, x equals negative 1.
Negative 1, 0, and 2. Do you see that? So let me explain again. Where is it differentiable? It has to be continuous
And not.
and not have a corner, cusp, or vertical tangent.
So everywhere except negative 1, 0, or 2.
Right. So if I say at what domain point, so now I want intervals. So from -2 to 1. Thanks, -1. And then -1 to 0. And then 0 to 2. And then 2 to 3. And we just include the endpoints.
In the back of the book, it tells us to write it like all points except. So what?
That's a, either one's fine. I like the interval notation because that's how I'll ask on a, usually ask on a quiz or a test, is interval notation. If you wrote it like that, it's fine. It implies the same thing. All right. Where is it continuous but not differentiable?
IDT.
No, there's only, okay, so wait.
None of them.
It's not continuous here. It's not continuous here. But it is continuous at -1.
Why can't it be? Oh.
It's a corner,
cusp
right?
or a corner.
Right here is a corner.
Gotcha. Is that it?
So where is it continuous but not differentiable? Not at x equals -1. So you would say, oops. Why is it? Sorry. Sorry, guys. Just right at x equals -1. Because that's the only place where it's continuous but not differentiable. And then how about the last? Where is it neither continuous nor differentiable? X equals, good. All right, questions there? Okay. So now we have a couple examples. We want to I'm giving you functions that fail to be differentiable at x equals 0. So what is the problem? Is it a corner, a cusp, vertical tangent, or discontinuity?
First one's cusp.
First one, cusp? Yeah. Right? We have an even over an odd power. And again, you could just do a quick sketch of this and just verify that. How about 1 over x? Yeah, so this is actually a discontinuity. So vertical tangent is a function that is continuous. Remember, vertical tangents were something very specific. That was an odd root, whereas 1 over x looks like this. Right? So there's there's a vertical asymptote, but that's not the same as a vertical tangent. Does that make sense? There's a vertical asymptote, it technically doesn't have a vertical tangent. Okay? Yes?
For the cusp, does the x be to a power or no? Because wouldn't that be? I'm just confused about it. Wouldn't that be the 5th root of x to the 4th?
Yeah, that's okay if it's written that way.
Or wouldn't that be a?
So you're saying if I have
Would that be a vertical tangent?
the 5th root, I don't know what's going on with me. I'm not doing anything. It's okay if you write it this way. You just have to be able to recognize if I give it to you in the root form, that these imply the same thing.
I'm just confused because the vertical tangent has an odd root too. Because of that.
Oh, just odd roots with just x to the first. Yeah, sorry. No other power, yeah. Okay, how about example 4? So find all values of x for which the function is differentiable. Okay, so there's a couple ways you could do if you have your calculator and you want to graph it, but what were the reasons why it's not differentiable? We said not continuous, corner, cusp, or vertical tangent. So let's take a look. Oh no, but you have to factor x to the 3rd minus 1.
That's not true because you already know where it's not continuous.
Good one. So, do we care about the numerator? No. We just care about the denominator. So these are discontinuities, right? It doesn't matter if it's a removable discontinuity or a vertical asymptote. It's still not continuous there. So where is it differentiable? Everywhere except those points. How about B? So this has an odd root.
So it's vertical tangent.
Okay, so this has a vertical tangent, but
just
where?
because it's 0.
Okay, but be careful here.
Negative
Oh,
2.
negative 2.
Oh, positive. So
Because-
positive 2 up 3.
If we were to graph this, it looks like this. You would have for right now, you could have a calculator for this part, it's fine. And you could see that it's going to have a vertical tangent right at x equals 2. So it's basically whatever your horizontal shift is going to be, that's where it's not differentiable. So from negative infinity to 2, and from 2 to infinity. Does that make sense? We're okay with that? All right. This is the last thing, right? Yeah. Okay, we're not going to really get into this much, but I just want to state the intermediate value theorem. So we did an intermediate value theorem for just regular functions. Do you remember that? IVT, just the regular one. So we said, like, let's say you have a function, and we said, all right, if you have a point here and a point here, then it's got to take on all the y values in between. So for example, if I know I have an f of a is like at -2, and this is at f, let's say f of b equals 3, then some point in between there, it's got to equal 0. It's got to cross the x-axis. We went over it briefly. It's something that we'll see a lot more later on when we get into some of our multiple choice questions. But this is also true for derivatives. So if you have f prime of a, let's just say you take a point. Let's say we'll take this point here. And you look at the slope here. I don't know, what does that slope look like? Maybe 2. So let's say this is m equals 2. And then let's say this point here, m equals 0. That means between here and here, m has to be equal to all the values in between. So at some point, is there a slope of 1? Yes. At some point, is there a slope of 0.5? Yeah. At some point, is there a slope of 3? No. So we know that if this is the tangent slope here, and this is the tangent slope 0, that it takes on all slopes in between those two values. The intermediate value theorem. Okay, so are we feeling worried about the quiz? What do we have? There's nothing to worry about. There's no practice quiz available. I don't always give practice quizzes. So, yes, your homework.
Should be doing it, you know.
So, what is your quiz? So, what's the quiz going to look like? I'm going to provide you with the formula. I want you to know the alternative definition of derivative, the f of x minus the f of a. Okay, that one. So,
That one you're giving us, or that one?
I'm going to give you the formula.
Okay, sure.
So, if you think back to,
Do we have to use it?
yes. Here, let me go back to your notes. I'll show you what you need to know. So obviously the notation you need to know. Okay, so if I just say d dx and then you come up to me and you say, well, I don't know what that means. It means take the derivative. Okay.
Does that all just mean derivative?
It all means derivative, just different notation. Okay, this you should know from the last chapter, right? Okay, so that's not new. All right, and being able to apply it. This is the one, because I want you to specifically use this formula, I actually give it to you on the quiz.
So
Okay,
we
so
don't
this
need to
is provided. What's that?
We don't need to know the other one?
Well, you should already have the other one memorized.
But yeah, but like,
Yeah,
we're not going to be
so-
using that one on the quiz.
This one.
Okay.
Because
Only this one?
only this one.
God.
Because you were already tested you on the old one. Okay.
For sure.
So if you want to use this one, and then if you're used to using the one with age approaching 0,
Yeah.
you could do that on the side or on scratch paper to check your work. That's fine. So if you don't feel comfortable with this one, you still have to show me that you can use it, but then you can check your answer. Okay? What is going on? Let me go with this next. computers.
We only have
My
physics one.
computers acting strange.
I know, but it's extended.
One-sided derivatives. Again, this is where the one-sided derivatives, you need to be able to kind of compare. You need to be able to see the corner cusp vertical tangent, which one, okay? And understand the concept of differentiability.
Oh, I have a question.
Yeah.
So, like, for physics, we're allowed to plug stuff into our calculator because, like, on the exam you are. Is that the same thing?
Is
Like, certain definitions you can, like, write in your calculator. I mean, for AP, they've always told us, like, it doesn't really matter.
right. So you have your calculator.
I can do whatever I want.
You can put whatever you want on it. You could put formulas on there, that's fine. But then again, that's why almost all your tests are part no calculator and part calculator. And same for the AP exam. They know that you could put any formulas on your calculator. You can put all the derivatives on your calculator. You put all the rules. The only problem is it's not so time effective if you're constantly looking through your calculator. Sometimes it works, and other times it if you feel comfortable doing that. Tomorrow we're not going to have it's not going to take the whole period. So we're going to go over homework first, make sure that we're clear on homework, and then we have the quiz. The quiz is like honestly like 20 minutes. It's like a 20-minute quiz. Gillian?
Is the AP test you have to show work on?
Yes, on the free response. You have you have a multiple choice and then you have free response questions. Not for a while. So calculus is different in that I can't even give you a problem, a free response problem. It would be impossible for you to do because almost every free response problem has derivatives and integrals intermixed, like they're mixed in together. So you would get to part A and you'd be done. You couldn't do anything. So unfortunately, we can't get to any AP. We have to cover the curriculum first, and then we do AP review. Of course, there's going to be like some multiple choice or some types of questions mixed in. You guys will be prepared. I don't know.
So excited.
No calculator, the whole thing, or part of
Let me.
Can we use calculators on our quiz?